Today we are going to do section 9.5. Okay, so first let's look at the book. We have, this is page 298 and 99, which we have already done, but I want to redo it anyway, just for the principle, but not take too long at it. That should be good enough. Next, page 300 and 301. Let's see, here's the entire page. And then a bit closer on the top. Anyway, closer on the bottom. Okay. And lastly, page 302 and then 303. There it is. Okay, and then top and bottom. That should be good enough. So let's begin on page 298. We have, in this section, we're going to talk about something called uniform convergence. And what happens is now, instead of just a regular series, we're going to consider a series of functions. So in a way that the function is defined such that each x of the function has its own infinite series. So for each x, we plug it into the formula and add it all up, okay, to infinity, and that gives us the f of x, which is one of the values. Then for the next x, we do the same thing. So the function itself is an infinite series function, and it looks, of course, like that, see? So for each x, we plug it in and add it all up, and of course, it better be convergent, or otherwise your function wouldn't be defined. So whereas in talking about this kind of function, then we assume that it is convergent, okay? And now being that this kind of function need to be convergent for each x, we consider something that's called uniform convergence, which means that the function is convergent in a systematic manner, and we'll explain that in a moment. And let's see. And the reason for that is, with this, if we expect it to be convergent in a systematic way, then we can study things like continuity or the sum of the functions. Well, anyway, the continuity anyway. So that's enough. Let's move on to the next page. Now, to study any kind of infinite sum, first we start out by considering the partial sum, which is finite, right? All infinite sums are defined as the value of the partial sums as the limit goes to infinity, if that limit exists. So the partial sum of such a function, of course, will be the first part, which is calculating the sum from k equals to 1 to n of uk of x. Now with this partial sum in mind, then let's consider definition 5, which is the definition of uniform convergence. The series, that is the f of x that we've been talking about, it converges uniformly to f of x. That is, the sum of ukx converges uniformly to f of x in some set closed interval. And if, what that means is, given epsilon bigger than 0, there is an integer m that such that as long as the n is bigger than m, then f of x and Sn of x is going to be less than epsilon. That is, if we consider that we have the function f, which is like over there, right? And then the S of n is somewhere close to it, and for during the entire interval from a to b, the difference of them has to be less than epsilon. for the all of x's, okay, as long as n is big enough. If that is the case, it is called uniform convergence. There are cases where this thing doesn't work that way. For example, it might be close in some places, f, and then here's f of x, and then it might be close somewhere, and then it goes up or something. And in other words, it's not allowed to do anything weird like that. That is, if we're going to be, if Sn of x is called uniform convergence, then it uniformly gets close to f of x, and without doing any odd thing in the middle or ends, doesn't matter. If that is the case, then this is called uniform convergence. So everybody gets in line within epsilon, okay? So basically, once you announce a large enough m, then every single point in here, every single point on the partial sum had better be within the allowed range. Again, allowed epsilon bigger than 0, no matter how small epsilon is. Now, specifically, let's consider that normally, if you consider each x, this statement is true. For each x given epsilon bigger than 0, then we can restrict it to be small enough if m is large. The difference here is that, so in general, m is the m where function is within epsilon is dependent on both epsilon and x, okay? But uniform convergence means m is dependent on epsilon only. All x's has to fall in line, okay? They're like the entire troop, the entire troop over there. There is with no exceptions. And if that is the case, then the function is converging uniformly. So first, let's consider an example A, where we consider the geometric series. Geometric series converges uniformly and a equals to 1 over 1 minus x, as we know. In a range, if the range is less than 1, okay, it converges from minus a to a, if a is positive and less than 1, as we know. Now, in this case, then Sn of x is going to be equal to 1 minus x to the power n divided by 1 minus x. The reason for that is, I have that written down here. Okay. Now, as we remember that the sum of xk is, well, at least the partial sum is equal, if you write it out, will be x and x squared, x cubed, all the way to xn. As you might remember from algebra, that is the same as this, okay? Because if you take this thing, factor out 1 minus x, you get exactly that. So that's why the partial sum equals to this thing. So then if we calculate the hard way, fx minus Sn of x, which gives you this thing, and then do some algebra, which is this, and if x is less than a, well, anyway, then this whole thing is going to be bounded by this value right here, right, as long as x is less than or equal to a. So then if we have let's see, what is that? If we have epsilon, just pick this thing to be less than epsilon, okay? If it is less than epsilon, then for as long as the value is big enough, then well, we can work out some algebra here. And so as long as m, by the time you work out the algebra, it turns out m has to be bigger than log of epsilon, etc. As long as m is big enough to make that happen, and then the whole thing is uniformly convergent. So please do this yourself. A small bit of algebra shouldn't take too long, okay, to confirm what the book says. And this is what the book says. That let's see, where is it? Yeah, the book says that if to make this thing less than epsilon, we just work on some algebra and figure out that m has to be greater than this value, and then everything will come out. And then more importantly, this thing has no x in it. So it doesn't matter what x value is, this will be true, okay? As long as m has that relationship with epsilon. That's all that matters. So as a result, we know that the sum of x to the power k is uniformly convergent to wherever it's converging to. And so that's example A. Next, let's consider example B. I am looking at the wrong page. There. Okay, example B, we have this odd-looking thing. Okay, that is, what is it supposed to do? Well, this is to show us that just because a function converges, infinite, the sum of UKX converges to f of x, doesn't necessarily mean it is a uniform convergence. You might think it is because each one has to get there, right? I mean, so why wouldn't it be? And every x has to get there, plus this range is closed. So there is nothing is taking off the infinity or anything like that. So how can it possibly be that something that converges but yet it's not uniform? And here's a cute little example to show you why that is the case. Okay, and we'll prove it, show you without a doubt. It's very, very neat. So let's look at this function. What is that? We have a bunch of weird looking things, right, that looks complicated with e and k minus 1 in there in example B. And it converges. So first let's prove that it does converge on some interval. So to do that, let's write it out, okay, the partial sum, to see if it even converge. So here's the example, example B's series. And then if we write it down, starting at k equals to 1 and all the way up to k equal to n, you notice that this it equals to this pile of stuff, and very soon you notice the minus 1, the green one cancel out the green one. And the next, the red one, cancel out the red one. And we keep doing that until there is only this one left. So S of n only equal to nx e to the power negative nx squared. So that's so the function is telescopic, so to speak. That is, it has internally subtracting itself all the time and subtracting itself out. So Sn, with that logic, equal to as the book says, Sn only equal to one term, okay? And as you can see, Sn is equal to this thing right here. And what's more, the limit of Sn as n goes to infinity is f of x. That is this whole function, okay? If f of x is defined as a sum of the series of functions, this is f of x. And what is f of x? F of x is calculating this thing, being that this is Sn, as n goes to infinity, and when you stare at that, as n goes to infinity, this thing is going to be 0. Being that e it has a negative exponent, so it's dying fast. Okay, so the whole thing is collapsing into 0. And so which means the series of this function actually converges to 0. So it's basically much ado about nothing, right? You have a bunch of functions and they're all just going to converge to 0 anyway. Then let's look at the next page, page 300, and see what happens. Now, does this function converge uniform? Is it a uniform convergence? From 0 to 1. So we're not asking much. We're just going from 0 to 1 is all. And well, if it were, let's say it is, okay? Now, if it is uniform convergent, then if we are given, by the definition, we are given as some epsilon, say epsilon equal to 1, okay? We pick a very big, nice epsilon, lots of space. Then f of x minus Sn f of x, which is nx e to the power negative nx squared, and will be less than 1. Remember, why is this equal? Because f of x is 0. Remember that, okay? Because f of x is the limit as n goes to infinity of the partial sum, and it equals to 0. So the difference each time is equal to exactly this thing. And then the next step is, step 4, is the maximum of this thing is actually equal to square root of n divided by some number. And the maximum of this value, which means as n goes to infinity, the maximum is going to be bigger than epsilon. It doesn't matter what epsilon is, because being that this is going to infinity, as n goes to infinity, then there is no way that this can be contained by any kind of given epsilon, whether it's 1 or something else. So that is what this says. Then we have a contradiction. Now you might wonder, what does that mean? That means the distance between f and Sn of x is going to infinity. That is, the distance as n increases, the maximum distance between these two is getting bigger and bigger and bigger, okay, and actually stretches to infinity. Now, how is that possible? So I plotted this thing out to show you. If you plot it out, then you will see why this is the case. Now, here's a plot, okay, of some examples where I have plotted the red line is where n is equal to, I think, 1, right? And then so x minus x, ex, e minus x squared. And then the green line is where x is now 10. Okay, so as you can see, it's going up. And then the blue line or purple, whatever that color is, blue, I think. The blue line is when n is 100, and you notice now it has risen dramatically. And then as the n increases, this is going to get bigger yet. Okay, and I just have 3 examples to show you exactly how that works. Now you might wonder, well, if that's the case, is this thing actually converging to 0? Yes, it is, because if you pick any specific point, you will notice that, for example, I pick some point over here. Okay, now the first point is on the red line. That is right there, right? The second point is on the green line, so it got up. The second point got up, but by the third point, it has come down. You see, so the third point on the blue line, it has actually come down below the red line. As you can see, it will eventually go to 0. So any specific point in here will go to 0. Okay, it's just that it might go up first. It will, I mean, it's not a matter of might. It probably go up first and then go back down. So basically, the graph is being pushed to this side. Let's see, where am I pushing? Yeah, this way. So we start here and push the graph, keep pushing it that way, so that everything over here is being pushed down to 0, okay? But everything over here being squeezed higher and higher, but we don't care. We just keep pushing so that until we get past every single number here that's bigger than 0. Then and it will all, so every single number will go to 0, but it will go to 0 at vastly different times. See, like as one guy over here is as one guy over here is going to 0, that guy over here is getting huge. But doesn't matter how huge he is, eventually the line will push past him, and then he will also go down to 0. So that is why this is such a neat example of how you can do that. And you might wonder, what about 0 then? Well, 0 is just, if you plug in 0 into the infinite sum, that is just the limit at 0 is well defined. See, if you plug in 0, then everything else don't matter. It's just equal to 0, period. So so at 0 is it doesn't go anywhere. So but anything that's even remotely bigger than 0 is going to be pushed up to very, very big, and then come falling down afterwards. So imagine how cute this is. So basically, we're doing this pushing thing. So everything, as you push, this thing being squeezed up, okay? Because you're pushing this way, so there's less and less space. The area under the curve stays not exactly constant, but almost constant. The area under the curve approaches 1/2, I think, and which we will explore in the next section. But the point is, the area under the curve is not decreasing, okay? So it's still there, and as you push it, it's forced to go higher and higher, which is super neat. All right, so that is this graph. And the next thing I want to talk about, of course, is, I lost the page again. Oh, it's over here. Okay, the next thing is we need to do some details. For example, okay, the book says the maximum equals to that, which is true. If you plot the graph like I did, okay, this does check out. It does equal to, that is, what I mean is the highest point here. Each highest point, if you do the math, the highest point does check out to be that formula that's stated in the book. Okay, and so it's right here. So the highest point is, if you calculate it, the maximum is exactly this thing. And how do we calculate the maximum? Well, we use the same trick from basic calculus, where you take the derivative, set it to 0, and all that stuff. And yeah, which I have done right here. Let's see. Where's my function? Yeah, okay, so to calculate maximum of this thing, we have g of x is that, so I calculated the derivative, set it to 0, figured out that x has to be this, and plug it in, and don't make a mistake like I did, and then eventually you come up with this thing, okay? So it does work out that the maximum of each sequence is, each partial sum, Sn, is the maximum is going to be this value, and what matters about this thing is that this is going to infinity. So the function is converging to 0, and yet part of it, part of the sequence is going to infinity. Is a very odd and situation that's counterintuitive, okay, which is what makes it super interesting. So that's that. So that is the example of how a function can be convergent into something, but not uniformly convergent. Yeah. So let's see. Okay, next. I should mention what's underneath. Underneath, we have a simple little graph here, which is not different from what I've drawn on the board, but it has so if you have a function that f of y equals to f of x, you have a one that's plus epsilon that's on top, and the one that's minus epsilon, f of x minus epsilon that's on the bottom, and then the partial sum is going to be in between, okay? Well, at least it's supposed to be if it is uniformly convergent. And for all partial sums that's bigger than a certain set number, that is given epsilon, there's a set number m such that every partial sum past it and is bigger than m, then it has to be locked in within that range of fx plus epsilon and fx minus epsilon. So, and the example B being that our function Sn is completely going nuts, right? It cannot be contained for all large n, and even if epsilon is big, so then being that its height is going without bound. All right, so that is that. Let's look at next. So example C, we're still on page 300. And let's look at example C, where we have this interesting function, which is the function is made out of a bunch of convergent functions, a sum of convergent functions. However, here's a weird situation happening, that is, it converges into, even though it's a bunch of continuous functions and that converges, it converges to two different spots. And that is, it converges into a discontinuous function. And the function will be equal to 1 for x that's between 0 and 1, but not include 1, while it converges to 0 as when x is 1. Okay, there's a slight twist there, and finally the whole thing just did that. So as a result, f of x is not continuous, which means there is no way that the Sn can be uniformly convergent to f of x, because to be uniformly convergent, you have to be close to the discontinuity. If you have a discontinuity, then the Sn has to be close to both points, which is not going to happen. Okay, and the book also gave a analytic argument, which I think is not really necessary. It's pretty obvious. I mean, the function a convergent function can converge into two spots, and specifically this is referring to x equal to 1. Okay, when between 0 and 1, then everything converges okay. It's just that at 1, then it doesn't know where it's going. And so that's why it's not uniformly convergent. It does know where it's going. It's just going to a different spot. And there's only one guy that goes somewhere else. Okay, everybody else is going to one spot, and that one guy has been kicked out to somewhere else. Anyway, I believe there's a slight mistake here. Okay, where the function is equal to xn from 0 to 1, not including 1, and it equals to 0 at x equal to 1, not 0. Okay, and because it already says something about x equal to 0, so it makes no sense to say x equal to 0 again. So it actually equals to 1, and so please consider that and read the rest and get this to come out yourself. Okay, and to the author is trying to prove that it's not possible for it to be at two places at once. So, and next we are going to consider Weierstrass's M-test. Oh, I should first show you what I wrote down for example C, although I don't think there's anything really exciting that I wrote down because the situation is quite easy to figure out, well, because it is a telescopic situation. So everything works out nicely because it cancels itself out here, there, and everywhere. Next, let's think about, we're now on page 301. Where we're going to talk about theorem 11, the Weierstrass M-test. The Weierstrass M-test states that if we have UK, the absolute value of UK is bounded by MK, a bunch of numbers, and furthermore, so they are bounded, but MK might change. However, there's more. MK has the sum of MK has to be convergent. So MK is going to 0, right? MK is a very strict control of this stuff. And if under such strict control, then the series U of x, UK of x will converge uniformly. So this is the Weierstrass's M-test for uniform convergence. Now to prove it, let's let M equals the sum of all the MKs, and then Tn as the partial sum of MKs, adding from 1 to k equal to 1 to n, and then f of x, of course, is the sum of the original function that we're talking about. Now, if that is the case, first we need to prove that f of x actually does converge under the given conditions. Now, it does converge because it converges because each UK is less than MK, right? And the sum then is less than the sum, and the sum we're given to be convergent. So a series that's less than a convergent series, and then is automatically convergent, and that is but this has absolute value in it. Now theorem 7 on page 292 says if something converges absolutely, then it converges, and that is what we're using to prove. So here's theorem 7. Take a quick look, right? If a series converges absolutely, then it most definitely converge. So that is that's that. So we have shown that the function does converge. And so in other words, we know what we're talking about here. Okay, if the function doesn't even converge, then it kind of we're missing the point. So then. But the next job, that's the easy part. The next job, however, is that we need to prove not just that the function converge, that is, it means that it actually means something, and but it is also converging uniformly. So that there's none of that's pushing it and squeezing it up and goes infinity bit happening. It's not happening because MK is being, the whole thing has to be less than MK, and MK is going to 0, see? So we're not going to allow that weird situation where things are going to infinity, even as it's converging. And how are we going to prove that? Then let's look at this neat trick, okay? Then first we will consider the partial sum of f, or the UKs. The partial sum of UK will consider the two partial sums. First one, s of n plus p minus s of n. Now that would be equal to the sum counting from n plus 1 all the way to n plus p, because you subtracted out the tail end, which then, of course, is going to be less than the mk counting the same terms, okay? And the nk, and this will be equal to the, this is not less than equal to, okay? The book has less than or equal to, it's actually exactly equal to, and not that matters that much. And so this will be the partial sum of n plus p, right, minus tn of the mk's. And then so now we're going to pull the trick, which means we're going to let p go to infinity. If p goes to infinity, then s then turn into f of x, because that's where Sn is the partial sum of f of x, so it goes to f of x eventually. And then the Sn stays on this side. If p goes to infinity, then the partial sum goes to the sum of mk, which is m, okay? So that will be equal to m minus t over n. Now at this point, then we can say that if given any epsilon bigger than 0, we can just, being that Tn is going to m, right? Tn is the partial sum of the m case, so it's getting there. So giving epsilon bigger than 0, we can find n large enough, or find m such that as long as n is large enough, then the difference is going to be less than epsilon. And therefore, which means this function, the f of x and its partial sum, is less than epsilon for every single x. Being that we don't even talk about x here, this is true for every single x, and therefore the theorem is proved, which is a rather neat trick, right? How do you think of having these two things, right? They're both partial sums, but one is going fast, one is ahead of the other, and then you hold on to one and let the other go to infinity, and then it magically, the theorem gets magically proved. And so it's very cool. Now next there is example D, which is a short proof to show how it works. So please do that yourself. Okay, as the book says, just take mk equals to k to the power of -2, and you're home free. And so let's look at the next section. Now, there's uniform convergence, and then there's absolute convergence. Now, if the series is if a series converges uniformly, then it converges absolutely. Because converge absolutely just means the absolute value of each term. If you slap the absolute value on there, it will also converge. Well, but the theorem 11 is defined with the absolute value in mind. So if a series converges, then under this condition, the absolute value is already slapped on there. So then, of course, it converges absolutely. Now, that is if it follows the requirement of theorem 11, okay? If it doesn't, theorem 11 doesn't just say the absolute value is less than mk, and then the sum of mk, well, it also says the sum of mk has to be less than infinity. However, now read the next sentence carefully, okay? One might be tempted to suppose that all uniformly convergent series are absolutely convergent. But that is not necessarily the case. How can that be? Well, that's because this is a specific set of conditions that if a function satisfies, then it is uniformly convergent. But there are other functions that don't satisfy all the conditions here, but still are uniformly convergent. Okay, so this is so that the Weierstrass's m-test doesn't test everything. It's only applicable for some functions. So the rest might not satisfy all the requirements, and might still be uniformly convergent. And as a result, not all uniformly convergent series are absolutely convergent. Okay, there might be some that don't satisfy the Weierstrass m-test, but and therefore they might not be absolutely convergent, but they're still uniformly convergent. So example C, didn't we just do example C? Yeah, we did. Now example C is an example of something that is a series of positive terms. It converges absolutely, and yet it doesn't converge uniformly. We just have proof that that thing has ended up converging in two spots. And even then, it still converged uniformly, which is one example that shows that something that converges absolutely does not necessarily converge uniformly. Okay, so that is something to bear in mind. In general, the infinite series, you have to be very careful with it. What seems intuitive might or might not work. You have to go back to the principle all the time and follow the theorems exactly with all the hypotheses, and to make sure that everything is working out. Because what's intuitively appears that way might have a trap there, mostly because when things are going to infinity, our intuitions sometimes fail, and we have to depend strictly on logic. So next, let's go to the following page, page 302, and look at example E. Now, example E, we have yet a new thing here. Let me see. Now, example E on page 302, we have the alternating, what is this? Some kind of alternating thing, okay? And it converges uniformly on the interval 0 to x to 1, but not absolutely. Absolutely just means you can slap on the absolute value sign and still converge, which is not the case. Now, which is not true in this case. Now, at x equal to 1, the series is the alternating harmonic series, which converges conditionally, not absolutely, right? And it converges to log of 1/2. And then, let's see, but it cannot possibly converge uniformly because, it cannot possibly converge absolutely because if it slapped absolute value on this thing at x equal to 1, that becomes the regular harmonic series, which diverges. Now, let me see here. Now, to prove that this thing is uniformly convergent, and bearing in mind that let's see. This is an alternating series, okay? We are allowed to use corollary 8 on page 294, which I will show you right now. Corollary 8 on 294 states that for alternating series, then the difference between the limit and the partial sum is the next term. Okay, the difference in calculations is going to be less than the very next term, that the v of n plus 1. So with that, we can use that piece of information here. And so the difference of f of x and its partial sum is going to be the very next term, which is x plus 1. X to the power n plus 1 divided by n plus 1, which if x is restricted between 0 and 1, that's just less than 1 over n plus 1. So this difference is this proves that f of x is uniformly convergent, because this difference is going to be bound by epsilon, okay? Because as n goes to infinity, the difference goes to 0, so it can be bound by epsilon, and choose m big enough such that all future differences are going to be less than 1 over n plus 1. So that proves that this function converges in a uniform way. And of course, it doesn't converge absolutely. Now, this example also shows the limitations of theorem 11. That is, this theorem, even though this series does converge uniformly, we cannot, it is not possible to use the Weierstrass test to test it, okay? It's because the test can't test everything, okay? It only tests the ones we need. It only tests the ones that satisfy the pretty strict conditions. Nevertheless, it's still a useful test, of course, but we do have functions that are uniformly convergent, but doesn't satisfy the requirements of the test. So next, the last thing I want to say before we go do homework is this sentence right here, that the alternating series converges to log of 1/2. And now that was mentioned in problem 4 some time ago, okay? But we didn't do that problem, and because it wasn't proving it, it was just showing it. And now at this point, I decided that I will show you the proof that the alternating harmonic series converges to log of 1/2. And I found the proof on Google. And I will show it to you. I found 2 methods, okay? And they're very, very neat. The first method is right here. We have, so here's the alternating harmonic series, right? And we're trying to prove that this thing equals the natural log of 2. The first method is it involves several tricks. Trick number 1, we'll calculate s of 2n, the partial sum, the even partial sum, which means you do 1 minus and plus and all that, go all the way to minus 2n. Now rewriting that, that's the same as the one that you doing all the pluses, right, up to 2n, then subtracted by the even ones, and subtract 2 of them. So you subtract the first one out, and then subtract the 7 one so that it becomes negative, right? So that's the second trick. Now next, the third trick, we will have, so that is this thing multiplied out will be equal to that, okay? That is So then once we did that, then that is just the first n terms of this, the first part, okay? So once we do the subtraction, now we end up with n plus 1, and now the s to n goes from n plus 1 to n plus n. Okay, that's fine. And next, the next trick is even neater. You see, then we're going to factor out the n from the denominator. So the first term becomes 1 over 1 plus 1 over n. The second term is 1 plus 1 over 2 over n, and so on. It goes all the way to 1 over 1 plus n over n. So we are taking, factoring n out of each thing. Is a very neat trick. And then, and why are we doing this? Now let's look at the next page. Okay, and so when we have done that, then we can write this sum as this thing right here, okay, where k goes from 1 to n, you multiply by 1 over n, and so on. So that thing looks slightly familiar. What is that thing? Now we're going to take the limit as n goes to infinity, and what happens then? That is exactly, here's the last trick. The last trick states that if you do that, that is exactly the definition of the definite integral. That is, this is the definite integral of 1 over 1 plus x. If you let delta x equal to 1 over n, and xk equals the k over n right here, okay, and then that fits the definition of the Riemann sum over the interval 0 to 1. So you can so that is exactly that as n goes to infinity. Now how cool is that? Okay, I mean, who is gonna sit around and realize that kind of thing? But anyway, somebody did, okay, and so we can, now that we recognize that's exactly just happens to be, it's like finding gold. It just happens to be this thing, and then therefore it equals the integral, because it's the same definition as the integral, and which then we can integrate, and after integrating we realize that this equals the natural log of 2. All right, so and that is how the proof is stated. Since the partial sum equals the natural log of 2 as n goes to infinity, that is the original infinite series, which equals a natural log of 2. And notice that being the terms 1 over n is decreasing, strictly decreasing to 0. The fact that we're using s to n doesn't matter, because the odd partial sums s to n plus 1, which is just s to n plus this thing, okay, will converge to the same limit. See, share the identical limit. So that is that's taking care of a little bit of detail. Okay, since we're working only working with the S2n, what about the odd ones? Are they taking a hike? No, they're not. Okay, they're sticking right close by. So they are going to be the same one. And that is the first method of proving that the alternating harmonic series equals to natural log of 2, which is very cute, right? I mean, and I don't know about cute, but which is very cool, because it used 4 different tricks to force this thing into a very odd situation where it equals to the Riemann integral, and then the answer just popped out right in our face, which is awesome. Now there's a second method. The second method is calculating the Taylor expansion of natural log of 1 plus x. The natural log of 1 plus x, if you look up the Taylor expansion, it happens to be this thing, okay? And then more importantly, it converges from -1 to +1, not including -1, but does include +1, which means we can plug +1 in here, and that makes this side exactly the alternating harmonic series, and this side exactly equal to natural log of 2. And that is the proof, the second method, which is quite a bit shorter. So that is that. Now for homework, which is on page 295, if I can find it right here. No, wrong, that was the last homework. Homework on page 302. Let me write it down. All right, so for homework on page 302, please do problems 1 to 11 and then 13. All right, and I will not be talking about the homework, but I will show you what I did. The homework problems are all short. I don't think there's an exception here. or anything unusual that's worth mentioning. So I'm just going to show you the answer, max, whatever. And then that's it, okay? And so here is the first problems 1 to 8, I believe. Starts right here. Yeah, that's problems 1 to 8, and then problems 9 to 13. Yeah, which is right about here. And so please do your homework, and that is the end of this section.